In a 208 volts three-phase system, understanding how to calculate the volt-amps or VAR consumed by a load connected to a two-pole circuit breaker is crucial. This explanation will help clarify the voltage considerations and the impact of the power factor on the total VA. Consider a load connected to a 208 volts three-phase system that does not use a neutral connection, meaning it's only connected to two phases, such as phase A and phase B. If a two-pole circuit breaker is used to protect this load, and each pole measures 10 amps, the calculation of the VA can be approached in different ways, and it's essential to understand which method is correct and why. Firstly, it's important to establish the fundamental electrical principles at play. In a three-phase system, the voltage between any two phases, known as the line voltage, is 208 volts. The voltage between each phase and the neutral, known as the phase voltage, is 120 volts. Given that the load is connected between two phases without a neutral, the relevant voltage for calculation is the line voltage, which is 208 volts. The basic formula for calculating power, P, in watts, is P equals volts times amps, or volts multiplied by amps. Therefore, if the current measured is 10 amps and the voltage is 208 volts, the power consumed by the load is 208 volts multiplied by 10 amps, which equals 2080 watts. However, electrical equipment is often rated in volt-amps, VAR, which represents the apparent power. The relationship between watts and VA is mediated by the power factor, which is a dimensionless number between 0 and 1 inclusive that represents the ratio of real power in watts to apparent power in volt-amps. If the power factor is 1, the watts and VA are equal, meaning the load is purely resistive. If the power factor is less than 1, the load is reactive, involving inductance or capacitance. In this specific scenario, with a two-pole circuit breaker protecting two conductors, the apparent power, VAR, consumed by the load would initially appear to be twice the power calculated from the 208 volts and 10 amps measurement. However, this approach is misleading. The initial calculation of 208 volts multiplied by 10 amps equals 2080 volt-amps represents the correct apparent power of the single load connected between the two phases. Multiplying this value by 2, as in 2 multiplied by 2080 volt-amps, equals 4160 volt-amps is not accurate because it incorrectly assumes two independent loads, which is not the case. The circuit breaker protects a single load operating at 208 volts and drawing 10 amps. Therefore, the correct calculation considers the actual voltage and current experienced by the load. Now, let's address the question about what a power analyzer connected to the panel main would report. If the power analyzer is connected to measure the total power draw, it would measure the actual voltage between the phases, 208 volts, and the current drawn by the load, 10 amps. Therefore, the power analyzer would report approximately 2080 volt-amps, assuming a power factor close to 1. If the power factor is different than 1, the power analyzer would report the actual volt-amps based on the real power and the power factor. If the load has a power factor of 0.8, which is common for inductive loads like motors, the real power would be 2080 watts multiplied by 0.8, which equals 1664 watts. The apparent power, VAR, would still be 2080 volt-amps. This distinction is essential because power distribution equipment, such as transformers and conductors, are rated in volt-amps to account for the total current they must handle, regardless of the power factor. Therefore, in summary, the correct VA consumed by the load in a 208 volts three-phase system connected to a two-pole circuit breaker with 10 amps on each pole is 2080 volt-amps. It is crucial to use the appropriate voltage, which is the line voltage of 208 volts, and to consider the power factor when evaluating the real power in watts versus the apparent power in volt-amps. To further clarify the concepts, consider the following points. Firstly, always use the line voltage, 208 volts, when the load is connected between two phases in a three-phase system without a neutral connection. Secondly, the power factor plays a crucial role in differentiating between real power, watts, and apparent power, VA. If the power factor is not provided, it's generally assumed to be close to 1 for resistive loads. Thirdly, the rating of circuit breakers and electrical panels is based on the apparent power, VAR to ensure they can handle the total current, including reactive components. Now let's delve into some additional scenarios and examples to solidify understanding. Firstly, consider a purely resistive load, such as a heating element connected to the 208 volts three-phase system. In this case, the power factor is 1, meaning the real power in watts is equal to the apparent power in volt amps. If the heating element draws 10 amps, the power consumed is simply 208 volts multiplied by 10 amps, which equals 2080 watts or 2080 volt amps. Secondly, consider an inductive load, such as a motor, connected to the same system. Motors typically have a power factor less than 1, often around 0.8. If the motor draws 10 amps, the apparent power is still 208 volts multiplied by 10 amps, which equals 2080 volt amps. However, the real power is 2080 volt amps multiplied by 0.8, which equals 1664 watts. This means the motor consumes 1664 watts of real power but requires the electrical system to supply 2080 volt amps to account for the reactive power. Thirdly, consider a capacitive load, such as a capacitor bank, connected to the system. Capacitive loads also have a power factor less than 1, but the reactive power is opposite to that of inductive loads. If the capacitor bank draws 10 amps, the apparent power is 208 volts multiplied by 10 amps, which equals 2080 volt amps. The real power depends on the specific power factor of the capacitor bank. In practice, it's essential to use a power analyzer or a multimeter with power measurement capabilities to accurately determine the VA, watts, and power factor of a load. These devices measure the voltage, current, and phase angle between them, allowing for precise calculation of the real and apparent power. Additionally, it is important to note that electrical codes and standards such as the National Electrical Code, NEC, provide guidelines for calculating the load on electrical systems to ensure safety and proper operation. These codes specify how to account for different types of loads and their respective power factors. For example, NEC Table 310.15b16 provides ampacity tables for conductors based on their insulation type and temperature rating, which are essential for selecting the appropriate wire size for the load. Furthermore, when dealing with three-phase systems, it's important to balance the load across the three phases to minimize neutral current and improve overall system efficiency. Unbalanced loads can lead to voltage imbalances and increased losses in the electrical system. To balance the load, distribute the single-phase loads evenly across the three phases and use three-phase loads whenever possible. In the context of the original question, understanding that the load is connected between two phases without a neutral is critical for selecting the correct voltage for the calculation. Using the phase voltage of 120 volts would lead to an incorrect result. Always use the line voltage of 208 volts when the load is connected line to line. Finally, remember that the two-pole circuit breaker is designed to protect the conductors and the load from overcurrents and short circuits. It does not directly determine the volt amps consumed by the load. The volt amps are determined by the voltage and current supplied to the load, as well as the load's power factor. To recap, when calculating the VA consumed by a load in a 208 volts three-phase system, firstly, identify the correct voltage, which is the line voltage of 208 volts for loads connected between two phases. Secondly, measure the current drawn by the load. Thirdly, calculate the apparent power, VAR, by multiplying the voltage and current. Fourthly, consider the power factor to determine the real power in watts. Fifthly, use a power analyzer or multimeter to accurately measure the VA, watts, and power factor. By following these steps and understanding the fundamental electrical principles, you can accurately calculate the VA consumed by the load and ensure the electrical system operates safely and efficiently. Now let's explore the implications of different load types and the overall system. Firstly, resistive loads such as heaters and incandescent lights have a power factor close to 1.0, meaning the voltage and current are in phase. These loads consume real power efficiently, converting electrical energy into heat or light. Secondly, inductive loads such as motors, transformers, and fluorescent lights with magnetic ballast have a lagging power factor, typically between 0.7 and 0.9. The current lags behind the voltage due to the energy stored in the magnetic field. These loads require reactive power to establish and maintain the magnetic field, reducing the overall system efficiency. Thirdly, capacitive loads, such as capacitors and some electronic devices, have a leading power factor. The current leads the voltage due to the energy stored in the electric field. Capacitive loads can compensate for inductive loads, improving the power factor and overall system efficiency. To improve the power factor of a system with predominantly inductive loads, power factor correction capacitors can be installed. These capacitors supply reactive power to the system, reducing the amount of reactive power that must be supplied by the utility. This can result in lower energy costs, reduce stress on the electrical system, and improve voltage regulation. The size and location of the power factor correction capacitors must be carefully selected to avoid overcorrection, which can lead to voltage instability and other problems. A qualified electrical engineer should perform a power factor study to determine the optimal capacitor size and location. In addition to power factor correction, other measures can be taken to improve the efficiency of electrical systems. These measures include using energy-efficient equipment, such as LED lighting and high-efficiency motors, minimizing voltage drop by using appropriately sized conductors, balancing the load across the three phases, and reducing harmonic distortion. Harmonic distortion is caused by nonlinear loads, such as electronic devices with switching power supplies. Harmonics can cause overheating of transformers and conductors, as well as interference with sensitive electronic equipment. Harmonic filters can be installed to reduce harmonic distortion. It's also important to periodically inspect and maintain electrical equipment to ensure it is operating efficiently and safely. This includes checking connections for tightness, inspecting insulation for damage, and testing circuit breakers and other protective devices. Regular maintenance can prevent costly repairs and downtime. To further illustrate the concepts, consider the example of a small manufacturing facility with a 208 volts three-phase electrical system. Firstly, the facility has several motors driving various machines, resulting in a predominantly inductive load. Secondly, the power factor is typically around 0.75, resulting in significant reactive power demand. Thirdly, the utility company charges a penalty for low power factor. To improve the power factor and reduce energy costs, the facility installs power factor correction capacitors. Firstly, a power factor study is performed to determine the optimal capacitor size and location. Secondly, the capacitors are installed near the largest motors to minimize losses in the conductors. Thirdly, the power factor is improved to 0.95, reducing the reactive power demand and eliminating the utility penalty. In addition to the capacitors, the facility also implements other energy-efficient measures. Firstly, old fluorescent lights are replaced with LED lighting. Secondly, high-efficiency motors are installed when old motors fail. Thirdly, a voltage monitoring system is installed to ensure the voltage is within the acceptable range. As a result of these measures, the facility reduces its energy consumption, lowers its energy costs, and improves the reliability of its electrical system. In conclusion, calculating the VA consumed by a load in a 208 volts three-phase system requires, firstly, understanding the line voltage and phase voltage. Secondly, measuring the current drawn by the load. Thirdly, considering the power factor. Fourthly, implementing power factor correction and other energy-efficient measures can further improve the efficiency and reliability of electrical systems. By following these guidelines, you can ensure the electrical system operates safely, efficiently, and cost-effectively. Remember that consulting with a qualified electrical engineer is always recommended when dealing with complex electrical systems. They can provide expert guidance and ensure that the system meets all applicable codes and standards.